Okay, sorry. So without further ado, Sriram is going to tell us about dynamics of fractional quantum Hall effect.
Hey, thanks, Matt, and thanks for the organizers for having me in this wonderful conference. And so regarding the title of my talk, it's not periodically or quasi-periodically driven, but things will be time dependent and systems will be complex. So that's how I'm going to. Okay, so before I forget, so this work is done in collaboration with Gustavo, who was a postdoc at CCNY, but he has moved to a more long-term job at CUNY, and with Parmeshwar Nair, Paulo, Glorio. So I think he's at Stanford. This is a typo. And with my graduate student, Dylan Reynolds. Okay, so this work will involve hydrodynamics. So let me briefly give a overview of hydrodynamics that I'm going to use. So this is the hydrodynamics in a nutshell. So basically, let's say if you are interested in looking into a local agitated state of a system like this sinking ship, then you want to track its fate all the way down to its equilibrium state. So think of that as a proxy for a many body system. So these rats, which are just immediately flies off the sinking ship, can be thought of as like fast processes, which immediately go away as soon as the ship starts sinking. But the captains of the ship and the second captain and third captain, so on and so forth, are hopefully the slowly relaxing degrees of freedom which you want to track to learn something about the system as it goes down to its equilibrium state. So what is important in this caricature is that you want a scale separation between these fast processes and the slowly relaxing quantities, which are almost often the local conservation laws. And there are various reasons why such a scale separation happens. And it's quite remarkable that such a complicated many body systems can eventually be in long time scales can be defined by few partial differential equations and gives us enormous information about this. So we are going to ignore these rats, which are the fast time scales, and going to track few slowly relaxing important local conserved quantities. And it's not just happens in a classical system, this scale separation can happen in quantum systems due to some kind of a spontaneous symmetry breaking, or in superfluids, or due to quantum anomalies. And so this is quite a powerful tool to understand the near equilibrium dynamics of a system. Okay, so then for the purposes of my talk, the full hydrostructure is going to be set of conservation laws. So this is think of it as a captain, this is a continuity equation, and you have to supplement this continuity equation with a constitutive relation, which releases the flux in terms of the density and local velocities. And then you can also add another observable, which is like the momentum conservation equation, local momentum conservation. And then the momentum flux tensor can be given in terms of the velocity fields. And then this Tij is like the intrinsic stress tensor. And then in this case, for a compressible fluids, you need to supplement them with equation of state and thermodynamic information as well. And one more equation that will be relevant for my talk is that it's energy conservation. You can write a conservation law for a local energy quantity as well. And these dots are the rats, which have already equilibrated at some fast time scales, and I'm not going to worry about them. So this will be the hydrodynamics in a nutshell that I'm going to use. And then one example that everybody is familiar with and uses with or without their knowledge is like this classical fluids, which is modeled by some incompressible Navier-Stokes equation. So often in nature, the local density is not changing that much. So you can the continuity equation becomes like an incompressibility condition. That means there are no source and sinks on the velocity fields. And then the momentum conservation equation becomes like this famous Navier-Stokes equation with all its pressure terms, external forces, and then this is the shear viscosity term. And notice that one terminology I'm going to use later on in this talk is that in this equation, in this momentum flux tensor, the terms, if you see a term with one gradient of velocity field, it will be first order hydrodynamics. If you don't see any terms of gradients of velocity, it will be zeroth order hydrodynamics. So I'm going to use this terminology often in the later part of my talk. The zeroth order is with no derivatives of velocity in the stress tensor, and then the first order is something with one derivatives of velocity in the stress tensor. Okay, so since my title of my talk has fractional quantum Hall effect, it's a quantum system. So why am I talking about classical fluids? So a shortcut way of extracting anything quantum from these fluid dynamics picture is that you can think of these quantum fluids as classical fluids, but subject to some constraints. And these constraints are often imposed on some combinations of vorticity and density in the field. So one way to think about it is that, let's say you have a classical fluid and you want to lower the temperature of the fluid all the way down to 0 temperature. So most of the time what happens is that the fluid freezes into a solid, something else happens. But then there are very few cases which can survive in the fluid state all the way down to the ground state. And these conditions are almost like a rite of passage for these fluids to go through this all the way down to the ground state of a quantum system. For fluid helium, this constraint is that the vorticity of the fluid is 0. It was identified by Landau in 1941. For the superconductor, just like another form of charged superfluids, it's just like your vorticity shift pinned to the magnetic field. And this was identified by Abrikosov in 57. And for fractional quantum Hall effect, it's a bit more involved structure. And this combination of vorticity and density is a constant given in terms of these values. It was initially identified by Michael Stone and then later on generalized to include this function by Sasha Abanom. So another slightly more technical way to say this is that these are all the conditions upon which you can make the velocity Poisson bracket canonical. So these are all the ways you can make it canonical, which is what requires for you to have this state as a ground state of a quantum system. Okay, so let me just continue. So then you can linearize the system and then you can study the dispersion relation associated with this. So you can see that there are these gapped modes, the bulk modes, and then there is a third band, which is what is known as the omega equal to 0 mode, which is associated to some geostrophic balance. And an interesting artifact of this system is that it has some non-trivial Berry curvature. And so, but then typically in solid state systems, the Berry curvature is associated, often comes with the compact K variable, but here the K variable is not compact, it is extended all the way from -infinity to infinity. But still, even if the Berry curvature is localized at some point, you can define differences of Chern numbers, which are kind of valid description. So this Chern number written this way is the integral of this Berry curvature, and it's simply determined by the sign of F and the Coriolis parameter. And note that the sign of F changes as you cross the equator from northern hemisphere to southern. And that's why the equator is almost like a domain wall where some chiral modes are trapped, which governs our climate significantly. So this is the band structure, and then this associated Berry curvature in the heat map. Okay, so I'm not going to talk about the equatorial problem because it's not related to what I'm going to talk about later. But an interesting problem is what is called as the coastal Kelvin wave problem. So what this coastal Kelvin wave problem is that you take the previous system and then subject it to a hard wall boundary condition, almost like a coast. And this Vy equal to 0. So then this is the linearized equations from the previous couple of slides back. And then I'm going to subject this dynamics to this hard wall boundary condition. And what you see is that one particular solution is given by this Vy equal to 0 everywhere in the bulk. And then there is Vx is proportional to eta via the square root GH. And then this particular mode has a dispersion relation which is strictly linear. And it only depends on the sign of F. So more recently, David Tong has identified a gauge theory connection that if you identify the elevation to be the magnetic field and the eta u star to be the electric field, the effective action that gives you this equation of motion can be written as the Maxwell-Chern-Simons action. And the boundary mode is just the boundary mode of that Maxwell-Chern-Simons action. Okay, so then, so this is one story. Then why am I talking about this geophysics problem in a fractional quantum Hall context? So I hope to convince you that this is almost going to be identical, but except very crucial differences. So let me give you a brief crash course on the electrodynamics of fractional quantum Hall liquid. So a fractional quantum Hall liquid is like a 2D electron gas that is subjected to very intense magnetic field. And then semi-classically, you can think of these as little cyclotron orbits, but then towards the edge, they kind of cannot complete their orbits and then they just skip. But in a more electrodynamically, you can write the current equation in terms of the vector potential in this way. And then where J0 is just the density, and the density is just related to the magnetic field via this Hall conductivity term. And then Ji is the sigma xy epsilon ij e. Epsilon ij is just like the Levi-Civita tensor here. So then what you can see is that if you plug these into this continuity equation, it just gives you the Faraday's law. And then another thing is that notice that this there is a divergence of J, and as easy way to see the presence of anomaly in this term is that when you take divergence of J of this quantity, see the sigma xy near the edge takes a jump. So it's non-zero inside and zero outside. So this divergence will hit this sigma xy near the edge, giving you an extra term which is electric field alone dependent, and that's what known as the anomaly equation, which is related to this U1 charge conservation in this problem. And all this electrodynamics can be packed into this effective Chern-Simons action as an effective action. Okay, so then a more sophisticated theory of fractional quantum Hall effect, which is amenable to a fluid description, is what is known as Chern-Simons-Ginsburg-Landau theory, or a composite boson theory. And this composite boson theory is just like a bosonic field, complex bosonic field, which is kind of mimicking a condensate. And then you couple this to a statistical Chern-Simons term, which gives its anionic statistics. So there are different theories for fractional quantum Hall effect. There is composite fermion, which is very different from composite boson theory. So I'm going to take this composite boson picture for now, and then maybe draw a comparison with composite fermions later. And so one way to fluidify this action is through what is known as Madelung transformation. And the Madelung transformation is just take this bosonic field and then write it as some density times this phase. And one thing I'm going to do that is done differently in the literature is that typically the superfluid velocity is associated with di theta alone as the gradient of the phase. But I'm going to take a slightly different superfluid velocity, which kind of is shifted by some function of n, which is the density. So the advantage of this will be clear in the next slide, but the choice of velocity is in my hands in going from this action to the fluid description. And it has several advantages in terms of how you can view this fluid dynamics of this associated with this action. And another side note is that this action is identically dual to a fluid action that is written in terms of Klebsch potentials, but the Chern-Simons morphs into a very different topological term. So I don't want to get into Klebsch, but for people who know it, there is such an action that exists. There's a totally different starting point of a fluid action with topological term that gives you the same equations of motion. Okay. So then if you write the equations of motion in terms of this fluid variables, then what you get is this hydro equations that I have been flashing in various contexts. So the first equation is just the continuity equation. The second equation is the momentum conservation equation. Now notice that contrary to the previous equations of shallow water dynamics, this is what I'm going to call as first order hydrodynamics. And I'm going to write all the first order terms in red so that you can track it. So if you drop all the first order terms, you're going to go back to shallow water equations. And so I'm going to track what physics is transmuted from shallow water dynamics to this, and what are the differences brought on by the extra first order terms here. And this is going to be the focus of this. And notice that there is I mentioned earlier that how you take a classical system and convert it into a quantum system in a fluid sense, you have this Lagrange multiplier that is naturally arises. And that gives you that the vorticity and density combination is constant here. And this is not, I'm not putting this by hand. You can derive this from this Chern-Simons point. So there is a A0 parameter in this Chern-Simons field, and that is just a Lagrange multiplier. The role of this Lagrange multiplier is to simply impose this constraint, is also known as a Hall constraint. Yeah.
Can you go through the logic of getting
Yeah, these are saddle point equations of the action. Yeah. Yeah, nice in the sense that they're first order. So basically, if you have done this exercise of converting this into fluids, you will see that there is a quantum pressure term. And this quantum pressure term is like two derivatives of density. So this choice of velocity, what it does is that it cancels the two derivatives of density and trades off with one gradient of velocity. And that has a nice form because this is nothing but an odd viscosity tensor. So quantum pressure term in two-dimensional fluids is identically Hall viscosity if you identify the velocity to be that. It's just a frame redefinition here. And since I have spent part of my life thinking about odd viscosity, there are many results that we could import staring at this set of fluid equations than something with a quantum pressure term. And then we can also study the fluctuation. So there is a hydrostatics, which is the background hydrostatics of this equation, and then you can study fluctuations around it in the linear sense. Okay, so then I have not talked about the boundary conditions yet. So let's say consider this hard wall boundary or a coastal boundary conditions that I was talking about in this Kelvin wave problem. So there are two. So the first boundary condition is what is known as a modified no penetration boundary condition. So without any tangent electric field, this will be just the current cannot penetrate the hard wall vertically. But because of a topological term in this system, if you have a tangent electric field, it modifies the no penetration condition. What it means is that if you put a tangent electric field, it is going to drive the charges to the boundary. And then since this is where the first order makes first appearance, that in a first order hydrodynamics, you need additional boundary condition in addition to the no penetration. So in the coastal Kelvin problem, since it was not first order, I only needed to impose the no penetration condition. But here I need to impose another boundary condition. And if I want to impose without introducing any dissipation in the system, there are two choices. The first choice is known as no slip condition. So this is another advantage of this first order, that in terms of first order hydrodynamics, the boundary conditions that you get have names in classical fluid dynamics literature. It's called no slip or no stress. Otherwise, it kind of looks very ugly in terms of quantum pressure terms, which is like shifts the velocity to densities and all that. So let's look at what happens when you apply a tangent electric field subject to these boundary conditions. What happens is that all these charges go to the bulk and then that's it. The Vx equal to 0 just spins does not allow these charges to move. So this is not typically what you expect in a fractional quantum Hall fluid, that in fractional quantum Hall fluid, all these charges go from bulk to the boundary and then are carried as a chiral edge current. And that's what you see. But then this no slip boundary condition does not allow you to do that. So we rule this boundary condition out. Yeah.
So you're looking on scales, I guess, much larger than the effective wave function of the edge mode, which, I mean, put a carelessly boundary condition, that wave function will go to 0, and the velocity gets.
Yeah, exactly. So those boundary conditions are not compatible with the anomaly condition. And in literature, people have made this mistake of putting that boundary condition and I will go into this in more detail. So what happens to the next set of boundary condition that is allowed without introducing dissipation? That means variationally. So this is the no stress boundary condition. So this T is the T corresponding to the Hall viscosity, odd viscosity term that the first order piece. So this Txy, and in quantum Hall, the electric field also generates stresses. So this is like a more involved equation. So then in the presence of this boundary condition, now what happens is that the charges go to the edge, but then they are also carried away with the chiral current. So this particular no stress boundary condition, even though it's a hard wall, a quantum fluid sees it as another fluid and then flows as if slips away without generating any dissipation. And so let's dig deeper into this set of boundary condition. What is going on near the boundary? So this is the first boundary condition, that is the anomaly modified no penetration condition. And this is the full structure of the second boundary condition. So notice that Tyx, typically the first order gradients are dissipative. So because that's where you see shear viscosity in classical fluids. But since I have obtained everything variationally, this Txy is non-dissipative in nature. And hence you can identically rewrite this using continuity equation into this dynamical equation form. And which has this, which is just like an identical rewriting of an anomaly equation. So this fluid dynamics boundary condition knows about the anomaly equation. So basically we are deriving the anomaly physics with 19th century technology of just kind of following the fluid dynamics aspect of this problem. And as a bonus, what you can see is that what is the effective edge action that gives you this dynamics? It's nothing but the generalization of the chiral boson action. So this is the chiral boson action, and this is now coupled to the background density that is terminated at the edge. So if you vary this action, you will get this equation. Sorry. Another interesting thing that I want to mention is that note that the bulk had a continuity equation. So this was the bulk continuity equation. And then what I'm saying is that the boundary equation is of this form. And notice the difference between them. So this is like square root n. Let's say there is no Ex for now. So this happens at the boundary, and then let's say the fluid is here in the bulk. So how this equation interpolates to this equation near the edge is actually given by what is known as boundary layer physics in fluid dynamics. So there is actually a profile of n that looks like square root n, which is just the one-dimensional edge density, and goes into this bulk continuity equation. And this interpolating profile is the boundary layer structure of this fluid, which kind of knows about the anomaly dynamics in this problem. And for more details of this boundary layer structure, I refer to our paper where it has been discussed in detail. Okay, so now let's linearize this system. And I'm keeping all the electric and magnetic fields in this problem. And what you see is that the linearized system, if you drop all the red things, is just the coastal Kelvin wave problem that I discussed before. And I'm going to write the no stress boundary condition with the electric field in terms of this dynamical form rather than the TXY form, because it's a bit more intuitive. So now, if you solve this problem for the bulk and boundary, what you see is that there are actually two modes that are going in the same direction, and which is kind of bizarre and very upsetting, because if you're talking about a Laughlin state, you're kind of you can only expect one chiral edge mode, and that chiral edge mode fixes the chiral central charge of the problem, which is kind of sacred thing that you don't want to mess with. So why are there two modes, and is this a wrong theory? A hydrodynamic description is a wrong description of this fluid. So what's going on here? And this particular mode, the blue one is the Kelvin mode, because it's literally the mode that is there in the coastal Kelvin wave problem. And here I'm going to point out that in the literature, there are papers by Nagaosa and a couple of other papers who thought that this extra derivatives are not important, because they can always think about scales much longer than that, and dropped this and then saw the Kelvin mode as the chiral edge of the quantum Hall system. What I'm going to show is that this is completely wrong. So even though the bulk may not be, the higher derivatives may not be important for the bulk, but as you go near the edge, the derivatives of density become more and more important. And then it's going to play a fundamental role in how the anomaly physics carries out. So then how to rule out one of the modes if you can, or is there a way to rule it out? So it turns out that there is a way to rule it out. So you can again turn on this tangent electric field and see which of these modes carry the anomaly. And then another way to see this is that, remember that the way I'm going to solve this now is that I'm going to look at the first 5 equations, including this boundary condition. All these are homogeneous, and the fields are just packed into this new variables. So the only inhomogeneous equation is the last boundary condition. So one way of solving, which will be more insightful, is that I'm going to solve our first 5 equations and then plug the U in terms of rho, and then write an effective density dynamics at the edge and see if it is anomaly compatible. And so it's almost smells like a GHD type game where you have this U as a function of rho and its gradients, but then here the U as a function of rho and its gradients are given by the bulk equation plugged into the boundary. And otherwise it's typically calculated using Bethe-Ansart type. So then let's look at the Kelvin mode case. So in the Kelvin mode, this U is simply, you can read it off from the slide where I talked about the Kelvin mode. So the U is proportional to C with this C connection. So this C was square root GH in the Kelvin mode case. This is just the eigenvector of it. And then since the omega is strictly linear in K, so you can, all the variables are dependent on X minus CT. And V is 0 because that's the solution for this Kelvin mode. And it turns out that there is no bound solution for this problem at the edge. So if you plug this U into rho, you will see that because of the tangent electric field, there will be infinite depletion and infinite population at the two ends. What that means is that the only solution that is allowed is that the fields are just 0. So the rho 0 is the only possible solution, and rho 0 has to be 0. So that means that the electromagnetic fields are not able to excite this Kelvin mode near the edge. So that, in other words, it is not responsible for carrying the gauge anomaly at the edge of the quantum Hall system. But they have the another mode, which is the chiral boson mode, which is literally coming from the TXY boundary condition, which is anomaly compatible in the previous sense. What you see is that this has this nice gradient expansion, and then you can study the edge dynamics, which is like, this is the anomaly piece due to the electric field, and then this is the homogeneous part, which you can write it as a gradient expansion for eta. So this chiral boson mode is compatible with the edge anomaly. And actually you can just stare at this picture and you can immediately figure out that the Kelvin mode cannot be the edge mode of any realistic quantum condensed matter system, because this is non-dispersive. So typically when you talk about Hofstadter spectrum and all this, you always see that the mid-gap edge mode will merge with the bulk band in some way. And in order to merge, it needs to disperse at some point. But the Kelvin mode is completely non-dispersive for all Ks. And so this already was a red herring. So there are, in previous papers, people just dropped the gradient terms and then saw that this is linear dispersing in K. Okay, let's rewrite it in terms of chiral boson. So not all chiralities are equal. So that's the bottom line of this exercise. And so in the last few minutes, I'm going to flash some slides about because once you have this edge equation, what you can do is that you can run a standard fluid dynamics method called multiscale analysis to get the weakly nonlinear dynamics of these edge modes, just how people calculated KdV for a shallow water dynamics. And it turns out that if you run this calculation, the weakly nonlinear dynamics of a composite boson edge is given by a KdV equation. And this is like the nonlinear edge generalization of the fractional quantum Hall state. So it has this chiral boson structure, but we're able to generalize this chiral boson structure by coupling it to some background density. And this background density, once you systematically expand in some power counting scheme, will result in a KdV equation. And this is like a systematic derivation of KdV at the edge of Laughlin state, modeled by the composite boson. And then one more thing that you can do is that now you can ask this question, okay, so you have some edge U1 symmetry like thing, but for square root n, which is, I'm going to call it as a edge density. So now what you can ask is that if you introduce dissipation, can you introduce dissipation without destroying the U1 conservation? So how do you do that? So what you can do is that you can shift the current term in way and then constrain the form of this by second law of thermodynamics. And the second law of thermodynamics forces the leading order term to be dx square in nature of this current. And it turns out that if you do the linear analysis, you get this diffusion term here. And so you cannot, if you preserve the edge charge conservation, then the only thing you can do is that this packet can only diffuse as it propagates. And if you supplement this diffusion with appropriate fluctuations that makes it under equilibrium condition, and also add the most obvious nonlinear term here, then you will immediately see that this is going to give you a breakdown of diffusion and lead to Cartar-Parisi-Zhang universality class. In fact, there are some signatures of this. Yeah, I'm almost done. So there are some signatures of this in some old experiments. And perhaps it would be interesting to revisit these experiments in this context. So there was an earlier work by Paulo and Luca Della Cretas, where they started from this purely U1 hydrodynamics in 1D, which was anomalous, and showed that there might be some general conditions under which you can have KPZ dynamics at the edge. But in their case, they don't have a microscopic theory. The new thing that we are doing here is that we are starting from a microscopic theory. So all these constants are fixed by the bulk theory. So C is this velocity of sound, which is the interaction parameter in the bulk theory. All these terms, the coefficients are fixed by the bulk theory, and they are not like parameters that you cannot determine. Okay, so in the last few slides, what I'm going to show is that so far I have considered the composite boson picture of the Laughlin states, but then this is a snapshot from Janendra Jain's book, Composite Fermions. What you can see is that there is actually an equivalent picture in terms of composite fermions as well. And for Laughlin states, these are just, they probably give you the same answers for all the bulk things that they have investigated. But there is some interesting restriction because composite bosons are very easy to deal with in a fluid dynamical sense. But a composite boson, which is the effective theory of composite boson, is given by this Grassmann field with this half-level Chern-Simons theory. And there is no obvious way, at least there is no straightforward way to write down hydrodynamics there. So perhaps maybe there is a way to extract something about composite fermions starting from this picture, or how these two pictures can be reconciled from a fluid dynamics point of view. Do they have a common language in which they can be framed? Because on one side, we are able to generate a lot of results. In another case, I don't even know where to proceed in this direction. Okay, so in conclusion, we developed a first order hydro description of SQH fluids that includes boundary conditions. And we deduced this appropriate fluid dynamics boundary condition and to be compatible with the gauge anomaly. And which gives naturally this chiral edge dynamics. And it's also, as a byproduct, you get this fluid dynamical derivation of this nonlinear generalization of the chiral boson at the edge. So there are some experiments that are not explained by the Venn theory, which is just the bare Chern-Simons description without any matter in the bulk. But maybe we can revisit now, since we have matter in the bulk, it might be able to, perhaps could be able to explain some of the missing pieces of the Venn theory, which is just the chiral Lettinger liquid theory at the edge. And so you can also think about, we also discussed this connection with the Kelvin mode, pointed out an error in the literature where people have associated chiral edge of a quantum Hall with the Kelvin mode, but upon checking for the anomaly consistency, it doesn't work that way. And the dissipative edge dynamics seems to be of the KPZ class. And as I said, this has more information than the purely Chern-Simons based edge theories. And these are some of the future direction. Okay, thank you.
Hello, is it your questions? Right.
So what's the deal with the other chiral edge mode? Like, does it exist? Does it not exist? Does it contribute to heat transport?
It doesn't actually. So it's almost like a, okay, first of all, the way I see it is that this is an artifact of some symmetry in the theory. So if you look at the structure of this Kelvin mode, so the V is 0 throughout the bulk and boundary. So if you plug this V equal to 0 in the equations, what you see is that there is a Lorentz invariance in the remaining equations, basically. And then what happens is that if you supplement these two boundary conditions in this theory, what happens is that the Kelvin mode vanishes at the edge. So the fields vanishes, it exists, but the field vanishes at the edge. So you can ask this question, perhaps you can probe it in the bulk. And so there are two transport-like experiments that we investigated. One is the anomaly transport with the electric field and the dissipative correction. So there are no dissipative corrections to the Kelvin mode as well. So these are the two cases in which we showed that it's almost like inert under this condensed matter type transport scenarios. But maybe, and you can ask what are does it show in other models? My current understanding is that if you preserve the symmetry structure of these equations in the model, I think this mode will exist, but perhaps will not be, at least what we have shown is that it will not be probed by the two heat transport and the electromagnetic electrical transport cases, but maybe there are other ways where you can see, but its existence itself is like sort of fine-tuned and probably the artifact of the symmetries of this equation. That's why we are not saying we have discovered a new mode in this theory.
Thanks. I'm curious about experimental observables. So you mentioned edge magnetoplasmons as one option. And if I could measure the edge magnetoplasmon conductivity as a function of frequency, is there like a specific thing that should pop out? Or if I tune against some parameter, like what should I look for?
Yeah, so there is this experiment where they have seen that there is a power law, which they say is between 1 and 2. For KPZ, it's like 3/2. So the question is that maybe we can try to revisit them and try to nail down what is that number between 1 and 2.
Okay.
So that's the closest experiment that I can see in the literature.
Austin.
KPZ coupling determined by the
This
lambda
one?
dash?
So this coupling is put by hand actually. So the form of this coupling is constrained by second law of thermodynamics, but the coupling itself is, so the only thing that will be constrained by is the fluctuation dissipation relations.
So that gives rise to the D or the lambda dash and.
Yeah, so the D and the lambda dash, no, not the lambda dash, sorry, D and the
noise.
D is the diffusion, basically, which will be related to this lambda.
And so I guess I'm thinking of the thing which would determine like the asymmetry and in the KPZ, distribution functions and so on would come from lambda dash, I think. Yeah,
so the lambda dash is the microscopic parameter which gives you the nonlinear term. So this is related to this this is some complicated function of the bulk theory parameters. And I think it will be a function of this this velocity of sound that is related to the interactions in the bulk.
And it could be either sine or.
I see, that's an interesting point. I think it should be fixed sign. I don't know which one, but it will be fixed sign.
Thanks.
Yeah, because it should not lead to instability in these systems. So it should be
stable either way. But
there are various versions of this nonlinear term. You can rescale and put it anywhere. But so in the KdV equation, it's a bit more clear to us. How so this coefficient will be precisely the KdV coefficient for us, which is again the nonlinear term is the same in the KdV and the KPZ.
Yeah.
So the only thing is that this KdV dispersion is already, you have seen it where it comes from. It's from the K cube term, but the K square term in the KPZ case is kind of put by hand as the only thing that is not put by hand is the fact that the K square structure is there. So the dx square term is constrained by the second law and the form of this emergent edge U1 symmetry that we have.
Okay, any further questions? Okay, if not, let's thank Sriram.